Welcome everybody. Today we are going to have a talk by Laurent is a professor at the University of Besançon, and he's part of an institute which is a collaboration between the University of Besançon and Sistemas, and which is the Femto Institute. And he has been he has been collaborating with us, with Claudio, with myself, within the several European projects for quite a long time now. And he has visited us previously a couple of times, if I'm not wrong. And so most of you may already know him. And he's visiting us now for 3 months. So he's, I talked with him. He's upstairs anytime until the end of June. So, thank you for being here. Thank you for visiting us. And
okay. Thank you very much, Perry. So it's really a pleasure. Thank you for the introduction. As you have noticed, I'm coming back several times, so that means I really enjoy coming here, but also collaborating with all the people here. As Perry told, it's a long collaboration. We started in 2001 with the first European project, which was already concerned by this topic of chaos communication. Then we continued the collaboration in the frame of the second European project. And this is more or less, I would say, the conclusion of the 2 European projects. Between the 2, there were an intermediate conclusion, but now we have a more global conclusion, and thanks to the collaboration with all the people here in Palma, we were very happy actually to work on that project, and I hope I will show that we also had nice results and interesting one. After the talk, I hope it will still work, but I started, during my stay here in Palma, I started to do a few experiments, so one is already working. I hope it will still work after the talk, so if you want to come and see a few things about an electro-optic chaos generator, of course you will be welcome. It will be in the lab where PEP is working, in the electronic lab. And this is not directly related to the phase chaos generator I will mainly talk about here, but the architecture is very similar and the behavior are rather close. Okay, so this is the outline of my talk. I will mainly give some introduction and background motivations about electro-optic and chaos communication and chaos communications more generally. Then I will talk into the details of the electro-optic chaos communication systems. And finally I will conclude mainly on the most important remaining issue in chaos communication, which is security, and I will maybe also just give a few lines concerning the new recently started project Focus, which is also coordinated by people in Palma, like Claudio, and in which we hope that we will be also able to bring some experimental expertise and solutions for performing practically the so-called state machines. Before starting the subject of chaos communications, I would like to talk a little bit about our group in Besançon. I should conclude, and I think I forgot to press the button as people move. Let me first give a brief overview of the different activities we do have in the group in Besançon. So the Femto SK Institute is a rather big institute with 500 people. So I will talk only about the few 10 people with whom I'm working in the optoelectronic group. The optoelectronic group is belonging to the optics department, and the optics department is one of the 5 departments in the Femto SK Institute. We already have control theory department, electronic and time frequency measurement department, micro and nanotechnology department, whatever, many other things. But let's talk about the optoelectronic group. I'm mainly involved in the activity of optical information processing. In a more broader sense, this concerns practically optical chaos communications, nonlinear dynamics, but also quantum key distribution. Quantum key distribution is developed by my colleague Jean-Marc Nauler, and I think he also had very nice results during the last year. He was collaborating with a private company, Smart Quantum, and they offered a commercial product of quantum key distribution, very nicely operating one. We do have ultra-fast optics activity. These activities are led by our group leader in the optoelectronics group, John Dudley. They are concerned by supercontinuum generation, photonic crystal fiber properties, pulse characterization, nonlinear propagation in different media, and currently it will be very rough and very informal, but I hope that you will enjoy. So if we want to point out a few details about cryptography history, you can find some first encryption procedure developed by the Egyptian. It was a ribbon, actually, where different characters were written, and you can only recover the original text if you were running the ribbon over a cylinder with a given diameter. So the diameter was the key of the encryption. If you get the cylinder with the right diameter, you could read actually the text properly, because the different characters are properly put one after the other. The Greek did what we call steganography, so they had slaves like other cultures also, and they tattooed some message on the surface of the head, and then they were waiting until the air grew again, and then they send the slave to people they want to communicate with. And okay, it's not so fast compared to 10 kilobits per second, but apparently it was used. The Romans developed also the famous so-called Caesar code. Caesar used this code, as far as I know, during the Gold War in the former France, and it was a very simple alphabetic circular permutation. Then you also have the Vigenère code, which was intended to complicate a little bit the circular permutation using a practical key. So this Vigenère code was rather important around the 16th century, I think. Then, of course, cryptography was strongly developed during love affairs. You know, maybe one of the protagonists here, George Sand. She spent a few years, I think, in the island here. Mary Stuart has also had some stuff with cryptography. And of course, during World War II, the Germans developed the Enigma machine, and also a very interesting thing was the fact that the US Army had a very nice encoding system, which was based on a very small tribute of American Indian. They were speaking a language which was absolutely different than any other language, and if you were not educated in this small society, you could not understand the language. And actually, those Indians were also speaking English, of course, and all the communications were done using this special language. And apparently, it was never broken during the Second World War. The Japanese could never understand what they were saying on the radio, so that there was no complicated code, except that it was a very specific language. And finally, we also have information theory, which played an important role at the beginning of the 20th century and the half of the 20th century through the Vernon code. The Vernon code is, as far as I know, the only one which was proven to be absolutely secure. The only problem is that the key length should have some properties, among which one is it has to have exactly the same length than the message. So usually we do have a very small key and a long message. If you have a key with the same length than the message, and which has some statistical property, then your encryption system is absolutely sure, absolutely secure. Shannon also did a lot of work on cryptography using involving information theory. Of course, there was the big area of the nowadays computer, the digital information area, where public encryption keys appeared, and several algorithms were developed as standards for any digital communication systems. CDMA was also developed, and so on. And finally, we have the physics approaches, meaning somehow we go back to the standard analog world encoding system, which was developed from the Egyptians up to maybe Vernon, or So the purpose is here to use physical laws or physical properties to secure information. There are two main approaches. One is the quantum key distribution. This is intended not to encrypt a message, but to send the secret key in an absolutely secure way. And chaos communication, we will be talking about. So it is intended to use pseudo-random behavior of chaotic motions to hide some informations, digital informations, or any kind of other information. So that's it. But among all the different points, I think the one I like very much is actually the fact that cryptography for me is something like creating a language. You have to create a language which is meaningless for all. I'm talking about the Indians, but meaningful for only one person. So that's something maybe we could think about to improve chaos encryption system and so on. So it is meaningless. It means that it cannot be understood by any people except the authorized communicant. It has a noise-like behavior, so it looks like noise. So that's very similar to what we see when we look at first sight at chaos. Okay, and there are also another property which is diffusion and confusion, which is very close actually to the property of sensitivity to initial condition, which is well known for chaotic systems. So it should be meaningful. That means this language should be understandable for the authorized receiver, and that means that the procedure is necessarily deterministic. That's also a feature of chaotic dynamics. They are deterministic. So you need to have a decryption node, otherwise it's just masking, but all the information is lost. If it's really masked in a real noisy signal. So, and now why are we interested in optical dynamics for chaos communications? Of course, because we know how to produce chaos with optical physical variable. But it's also interesting from the application point of view, because when you are looking at the different physical layer or physical architecture of the communication system, you have the software level, you have the network level, and so on and so on. And the only level that cannot be protected, because it's not a digital one, is the physical layer. At the physical layer, there is no protection, meaning that anyone can access an optical network. You have commercial tools that are available just to pick the optical flow on the fiber, so it's a commercial tool that anybody can buy. So this physical level is not protected. And actually, in the history of cryptography, we could also talk about a few places that have been discovered close to fiber optic networks, especially under the sea as well. People discovered just doing maintenance on the optical fiber under the sea. There were actually some tools left or something left close to the optical fiber, meaning that it's not a legend. So it's not something to warn people that the wolf is coming and so on. So it's a real fact that it has been discovered that in some places there have been some attacks to access the data on optical fiber network.
You have photos of that?
Yeah. Not here, but I could show you. Actually, not after, I have to ask. I don't have it in my computer, but you have photos where actually you see the fiber network and the environment, and it's very easy to pick the information. Okay, and another interesting feature is that optical networks are naturally operating at very high speed, very high bit rate, so it's very important to have ultra-fast chaotic dynamics. Yes.
So, these tools, you can access the optical flow without breaking the fiber?
Without breaking the fiber.
Oh.
Yeah. It's really just picking a very small amount of light, so it can even not be easily detected by the sender. So the power at the receiver, at the standard receiver, will not drop. So it's just picking a very small amount of light, maybe amplifying a little bit. But then you have direct access to the zeros and the ones that are conveyed on the optical fiber. The optical systems are well known to be able to operate at very high speed, so it's well suited to modern optical communication systems. Also, the optical chaotic dynamics are well known to be high dimensional as well, since they are usually based on delay dynamical systems. and delay dynamical system have the property that the dimension, the phase space dimension, is infinite. And actually, as I will report in the next slide, there are indeed a few very nice setups in optics that can be well controlled and that are well known and that are explored in different configurations, like ECLD is external cavity laser diode, and Ikeda is a particular delay dynamical system also. So, delay dynamics in optics. The most famous one, I won't talk a lot because you have one of the best specialists in the world in this lab, so I don't want to compete. But this is only to give a few details about the external cavity laser diode. This is a laser diode, and this is an external mirror, so the time delay, which is giving the dynamics an infinite dimensional feature, is put at a given distance from the output facet of the laser, and we can collect the output light here or here. And the global behavior of this setup is well known to be chaotic in some particular operating conditions. People have explored this in many different situations. The external cavity laser is not always operated or explored using semiconductor laser, but you also have microchip laser experiments, fiber ring laser, which is not a stationary wave, but a propagating wave dynamics. And of course, you also have delay dynamical system with semiconductor laser, not only involving all optical feedback, but optoelectronic feedback, in the sense that it measures the light and it sends back the light on the injection current of the electrode. So it's not non-optical, it's an optoelectronic feedback, but this one is also involving, like in all the other cases, the laser rate equations to rule the dynamics. Let's move to another family of systems, or another class of system, which is based on the Ikeda ring cavity. This is the Ikeda ring cavity, so you inject a CW light inside, and what you could observe under some parameter conditions is a chaotic fluctuation of the light at the output. Inside you have a delayed feedback, it's a cavity, and here you have a kind of carrier medium which is changing the phase depending on the input intensity. And the input intensity is ruled by the interference condition between the incoming light beam and the feedback beam. So if this feedback beam is fluctuating in phase or even in intensity through this medium, and depending on the previous round trip in this cavity, then you might have instabilities and so on. This architecture is much more explored by our group, so we developed a lot of setup which is based on this principle, but of course which is involving not a non-optical setup like this, but an optoelectronic one. So this is the kind of conversion view of this Ikeda ring cavity. You can see that the interference condition here is represented by a two-wave interferometer. The output of this two-wave interferometer is delayed by a delay line, which is the round trip time here. Then you have an optoelectronic system which is able to convert the detected intensity of the interference conditions into a phase modulation inside the cavity, inside the arms of the interferometer. So you can change again the interference condition. Okay, you're just injecting a CW light beam, and at the output you can modulate the interference condition. So this is basically the way that the Ikeda ring cavity has been implemented by many different groups. So the Ikeda ring cavity is a rather old setup as well, but the first implementation were done by people in the US using bulk Optical cells and a birefringent interferometer. The first people to develop the integrated optics version of this Ikeda ring cavity are people in Germany. And then we developed in Besançon another setup very similar, which is based on wavelength fluctuations of a chaotic waveform, knowing that an imbalanced interferometer changes its interference conditions with respect to the wavelength. So if we have a wavelength tunable element, we can change the interference condition. So the experiments I would like to show you after this seminar will be concerned by this one. Actually, it will be an integrated optics Mach-Zehnder modulator intended to perform practically this interferometer and the phase change of the interference conditions through the electro-optic effect. Okay, this class of delay dynamical systems are ruled not by the Leader rate equations, but by a linear filtering, which is corresponding to the feedback here, to the electronic feedback, the conversion from intensity to phase fluctuations. So it's the electronic which is limiting the fastest time scale at which the system can fluctuate, whereas here the time scales are much shorter. They are ruled practically by the atom lifetime level in this medium, which can be very short, of course, but this is much more convenient to control experimentally. Okay, so let me tell you a few words about modeling of this Ikeda-like dynamics. Modeling is rather simple, but maybe not very usual for physicists. It's rather simple for people from the electronic engineering community, because actually the ruling of the dynamics comes only from a filtering effect. A filter in the frequency domain can be viewed as a differential equation in the time domain. That's simply the conversion between this frequency domain filtering function. We can see here a very simple low-pass filter, and the differential equation will be extracted from the conversion, the usual conversion rules from the Fourier domain to the temporal domain. So, what I represented here is another kind of representation than this one, but maybe more schematic, where you see what you need in your feedback loop to generate this Ikeda-like dynamics. You need, of course, a nonlinear function. This is practically, in most of the cases, the interference function. You tune the interference conditions, and you have the sine square function of the interference, of the two-wave interference function. You need a time delay. Of course, you don't need that a priori, but you will have definitely always the situation. Any physical system will always have a limiting time response time, and this will practically rule the differential process. And of course, you need also gain. If your feedback loop has two losses, too much losses, then you won't have any oscillation and it won't be interesting. The nonlinear function is represented here. We know that practically we can tune this nonlinear function. We can tune its amplitude through the gain, or we can shift this along the horizontal axis through some offset phase in the interference condition. Okay? And this is representative of this limiting dynamical elements. So when you write the equations, you only have to use the standard rules for the correspondence between the time domain and the Fourier domain. Multiplication by I to pi f is corresponding to a differentiation with respect to time. This is used to convert the linear filtering in the frequency domain into the time domain of the differential equation. You have an example here with a low-pass filter represented here, and you can see that the differential equation will be written like this, and it will be driven practically by the input of the filter, and then you only have to think about that the input is nothing else but the nonlinear delay transformation. So this is the input of the filter. The nonlinear function is a sine square or cosine square function, and it's delayed in time. It means the interference condition depends on the past value of the dynamical variable. Okay? A slightly different situation, which is not very different but with very different consequences, is the fact that in practice, when we are dealing with broadband communication systems, we cannot have such nice low-pass filtering. We always have, due to cutoff frequencies of amplifiers, we also have a low cutoff frequency. We do have a bandwidth which is corresponding of the spectrum of the information to be conveyed, of course, but this starts at a few tenths of kilohertz, and this can go up to a few tenths of gigahertz. So you have several orders of magnitude, 6 orders of magnitude here where you can put information. And that's typically the filtering function which will be used to generate broadband figures. So the differential equation is slightly different. It's a second order in a very simple approach of second order bandpass filtering, and the time domain written with a driving term corresponding exactly in the same situation than the low pass filtering, where Z is the nonlinear delayed feedback term. Then the left hand side will correspond to an integral differential, so-called integral differential equation, where you have the integral term reflecting the fact that you have a low cutoff frequency, and differential term, of course, which is reflecting the high cutoff frequency. And the term D, as I told you, is the nonlinear delayed feedback in the loop. So, let's move now to electro-optic chaos communications. So, what we have been doing during this previous European project, it was first to investigate the properties of intensity chaos, and then we moved progressively due to the limitations, the practical limitations of intensity chaos, to another architecture, which is the main purpose of this talk, and which is the phase chaos architecture. So I will first introduce the intensity chaos, which is nothing else but the Mach-Zehnder delayed feedback loop systems, which I will try to show you afterwards if it's simple. So imagine that your feedback loop is represented by a very simple view, which is called the nonlinear delay dynamical process. Okay, it's an input-output system, and if you take the output and you put it at the input, then you have the delayed feedback, the delayed nonlinear feedback. Okay, and that's the configuration of the emitter in chaos communication. You transmit practically the chaotic signal along the transmission line, and at the receiver side, the key of the encryption system is corresponding to this nonlinear delay dynamical process, where you have a given rule between the input and the output. If you view this in the time domain with a very simple view, it can be a convolution view, where h theta is practically the impulse response of the filtering I introduced previously, and this is a nonlinear delay function. So the output is simply the convolution between the impulse response and the nonlinear delay term. Okay? And if you indeed have replicated exactly the same process at the receiver side, necessarily you will have the same impulse response, the same nonlinear function, and you should get the same chaotic fluctuations at the output. And that's the way practically we perform synchronization at the receiver with respect to the chaotic waveform at the emitter. So when we put a message, the message is put inside the oscillation loop, as you can see here. Okay? Which means that the transmission is corresponding to the message superimposed to the chaotic waveform. But don't forget that this is also the input of the block at the emitter, because the message is added inside the oscillation loop and not outside. There are different techniques, so we use always this inside loop addition technique. And the consequence is that the receiver is very simple. The receiver, you don't have to change the receiver with respect to the situation without any message M. And you can simply realize that since we do have the same input for this block and this one, necessarily we should have the same output here and here. But here we do have the message, whereas here we don't have the message. So if we do a subtraction, we recover the message. And we remove the large amplitude chaotic fluctuation. Okay? This is practically the setup. I'm sorry about the quality of the drawing, so I should have redo a little bit this to improve the resolution, but typically this is the delayed feedback loop with the Mach-Zehnder modulator, the nonlinear function, the delay, and then the optoelectronic feedback with the gain. Okay? You have the same elements here, except that you can see that this pass is practically present here, but it operates as an open loop configuration. Okay? Meaning that this output should be similar to this one. Okay? And here we have also a photodiode which is making a direct detection and which is intended to detect practically the chaotic fluctuations and the message. Okay? And here we perform a subtraction. The subtraction is performed practically when operating properly at the symmetric point of the interferometer. And here we practically have the opposite sign with respect to here. But we performed this, and we succeeded in recovering practically the information that was added at the emitter. This is practically the results we had at the end of this first European project. We did some suitcase where we put all the devices inside. You will see in the experiment that actually it does not take a lot of place, so it can be even reduced. So it's a transportable setup which we use to make some field experiments in Athens. And that's typically the signals you can see on the oscilloscope when you are plotting the evolution of a pseudo-random bit sequence. This is corresponding to the 0 level, and this is corresponding to the 1 level. Since we do have an information with a relative randomness, you have random switching between the level 1 and 0, but this is, of course, in synchrony with the clock of the message. If you mix this original message with the chaotic waveform, you can see here a bifurcation diagram. We mix this signal where we do have a chaotic motion. At the output, you will have a strong superimposed fluctuations, which is a pseudo-random fluctuation. Okay? At the receiver side, you have the same bifurcation diagram, but with a minus sign. The colors are inverted to illustrate this fact. And practically, the receiver is able to remove most of this chaotic fluctuation that has been used to mask the information at the emitter. And you can see that we recover a level 1 and a level 0, meaning that you can define a threshold above which you have 1 and below which you have 0. So this experiment was rather successful. We demonstrate 3 gigabit per second, but with a bit error rate which had approximately 10 to minus 7 or 10 to minus 5 over 100 kilometers. And this was really the limit. We wanted to upgrade the setup to 10 gigabit per second, but we faced a lot of problems. And that's the reason why, during this second European project, we tried to think about potentially more efficient architecture. And that's the electro-optic phase dynamics which came out. Why? Maybe a very general reason is a well-known fact that frequency modulation has a much better quality than amplitude modulation. So if you, maybe you don't know anymore what amplitude modulation is, because all the emitters are frequency modulated usually nowadays. Sorry. The main advantage of amplitude modulation is the fact that you can send over long distance in free space. With frequency modulation, you can only reach short distances, meaning that it costs a lot if you want to cover all the territory, all the space. But now we are in a rather highly evaluated society, so we have plenty of emitters everywhere, and we can modulate the frequency everywhere, and then you receive properly your favorite sending music on the radio, and thank you very much. So that's a well-known feature of frequency modulation. It has better quality. And frequency modulation and phase modulation is not so different. So that's the reason why we were expecting to have better results using phase modulation instead of intensity modulation. Okay, so let's move to the setup. The setup is, at the first sight, completely similar. But at the second sight, there are strong differences, and you can see this in the behavior, in the dynamical behavior. Similar in the sense that we do have a two-wave interferometer, but it's an imbalanced interferometer. The imbalancing is introducing the time shift, the time delay, delta t, which is rather small. In typical phase modulation or differential phase shift gain modulation, this time delay corresponds to the duration of the bit to be transmitted. If you have a 10 gigabit per second, then you will have 100 picoseconds time duration, okay, to recover properly the bits at the receiver. But you also have an electro-optic device, but you modulate the phase, not the intensity. You were also modulating the phase with Mach Zehnder, that the phase was directly modulated in one arm of the interferometer. Now it's different. If you modulate the phase outside the arm of the interferometer, it does not happen anything unless you modulate fast enough with respect to this time imbalancing. Of course, if you modulate very slowly, the phase difference is exactly the same as the interference condition, and you don't observe anything, which is not the case with the Mach Zehnder. With the Mach Zehnder, you can modulate very slowly. You will have the corresponding slow change in the output intensity. Here in the phase, if you modulate too slow, nothing happens. But if you modulate fast enough with respect to this one, and practically we use this idea of differential phase shift gain optical modulation techniques, which is well known in optical telecommunications, to generate some variation of the interference conditions through the fast modulation of the phase with respect to the delta t. So we tried actually to use delta t as large as possible, so that even a moderately fast modulation can indeed change nonlinearly the output intensity with respect to the input phase modulation. So the equation will be slightly different, but before talking about the equation, let me show you this spectrum. This is the spectrum, the optical spectrum of the laser light, as it should be. And this is the same spectrum of the same laser light, but when this laser light has been seeded into this electro-optic phase scale generator. So you can see the spreading is huge. It is corresponding to the bandwidth of the electronic feedback, a few tens of gigahertz, up to 20 gigahertz. Sorry for the scaling, but it's a rather small scale, so you can see that the minus 3 dB bandwidth is most probably like this, so it's more than plus minus 10 gigahertz, definitely. That's it. So for the modeling, we still have exactly the same kind of modeling. The left-hand side is representative of the linear filtering, and the right-hand side is the nonlinear transformation function. At that time, the nonlinearity is called temporally nonlocal because it is not instantaneous. With the Mach-Zehnder modulator, the nonlinear function is instantaneously transformed when you change the phase. Here, you have to deal with two different values of the phase at two different times due to this time imbalancing. So this is the nonlinear function for a simple two-wave interferometer, but principally you can imagine that a physical key can be designed so that you have a multiple wave interferometer, and we do have right now in the lab in Besançon a three-wave. It's not N with N big, but we do have a three-wave, and we try to demonstrate that even with three-wave we can technology control accurately enough all the different physical parameters of this imbalanced interferometer to perform synchronization, encoding and decoding through electro-optic phase scales.
I have an idea. What would be the capital T in absolute time?
Capital T
is your mismatch, or delta T.
Oh, delta T is imbalancing.
Yeah, how much is an absolute numbers typically?
Typical number, so the experiment we performed here is 250 picoseconds. No, 400 picoseconds. In the three-wave interferometer we are exploring right now, we have 280 and 330 approximately. So that's typically it's several hundred times the picosecond. So approximately 10 times the response time here you have for the high cutoff frequency. So those are typical time traces and spectra which are illustrating the fact that we do have a strong multiple timescale dynamics. We have 4 timescales, it was just underlined. Theta is integration timescale, a very slow one, 40 microseconds approximately. This one is a delay, it's a few meters of fiber, approximately a few tenths of nanoseconds, 70, 60 nanoseconds. This one is the timing balancing in the interferometer. It's of the order of a few hundred of picoseconds. And this one is the response time of the electronic feedback, which is corresponding to the cutoff frequency of typical modern optical communication systems, meaning a few tenths of picoseconds. Okay? So you have 6 orders of magnitude and 2 timescales in between. And this leads to such kind of bifurcation diagram. This one is the simulation, and this one is the experimental one. So they are very close, so everything is properly controlled. That's very important to be able to reproduce this nonlinear delay dynamical process. You have also bifurcation diagram in the frequency domain. This is a simulation, this is the experiments. You can see that there are slight differences, which we can talk about, but this would be going into details, but we can explain this. And this is typical chaotic spectrum we can obtain with the setup, but in the RF spectrum, it's rather flat, up to 15 gigahertz. So it's well suited to 10 gigabit per second communication. Phase scales cancellations. So for phase scales cancellation, we will apply the same recipe. We will characterize the nonlinear delay dynamical process at the emitter. We will fabricate a second one as close as possible in the first one, and we will see how far we can replicate the chaotic waveform and cancel this, but in the optical domain. That's a big difference. Previously, if you remember the setup as a receiver, you had 2 photodiodes, and you subtract in the electrical domain. Here, with the setup, it's also very nice. We can do this in the optical domain. So, how does it work? This is the nonlinear delay feedback process operating on the phase, on the optical phase. We transmit here the chaotic fluctuations, and at the input we split the light beam into two parts. One part will enter a phase modulator. This phase modulator will receive a signal which will be intended to modulate with the opposite sign the same signal than here, to remove the chaotic phase modulation. This signal is practically obtained through the same nonlinear delay dynamical process. You can see the same interferometer with the same imbalancing, with the same offset phase to be tuned, static offset phase of the interference condition. A variable attenuator allows to have exactly the right optical power level, and then the electronic feedback is generating the signal to modulate the phase modulator. Okay? You can see that practically we change the output of the two-way interferometer so that we have complementary variations, and that means that this signal will be the opposite of this one. Okay? This is an experimental recall of the chaos cancellation. In black you can see the chaotic spreading of what is observed on the transmission channel, and in red it's what you observe at the output of this electro-optic phase modulator. So you have a cancellation over approximately plus minus 15-20 gigahertz of approximately 10 to 15 dB, which is far from enough to put between this level, the decoding level, and this level, the masking level, the information, the spectrum of the information to be given. Okay, that's typical eye diagrams we observed at 10 gigabit per second. You can see the corresponding signal hidden on the transmission channel. The architecture of the emitter and receiver are slightly different with respect to the previous situation. In the previous situations, we were only concerned by chaos cancellation. Here we want to add the information. The information is simply added through a cascade phase modulator. So meaning that here we apply a differential phase shift keying, a standard differential phase shift keying modulation as it is used in standard telecommunication systems. And here at the output, we also put the DPSK demodulator. Okay, we demodulate here, we convert the phase into an intensity to recover practically the binary message that was applied here. Maybe a small remark is that this system can actually be operated in an on and off mode with respect to the chaotic modulation. If you don't want to encode the signal, you just open the loop here, and you have a standard DPSK transmission. Okay? If you want to encode the signal, you just close the loop, and it works instantaneously. Okay, that's the field experiments we performed as well. So we demonstrated for the first time in Besançon, in France, close to our university. We have practically in our city a very old fiber loop network of only 22 kilometers, but we had access to the city hall of Besançon and to the technical room. I don't have the picture here, but it's room, plenty of fiber, etc. It was rather nice. And we demonstrated on this fiber loop the first 10 gigabit per second chaos communication system. We also did some tests over a longer distance in Athens. You can see here the emitter and the receiver. It's rather compact, but it's an A4, typically an A4 aluminum board where we fixed everything to be able to transport in the city hall from the university or in Athens, in the plane. It's okay. It survives. This is the architecture. This is a typical signal observed after the transmission, before the decoding, and this is a signal observed after proper decoding. So, time is running, so I will try to go a little bit faster. This is mainly technical details about dispersion effects. That was especially explored in collaboration with Pierre and Modeste. Dispersion effects are very important, but they can be managed. That's the good thing. Using standard dispersion management techniques, we could really recover properly the correct spectrum to be chaos cancelled. But without this dispersion effect compensation, you can forget. You cannot recover anything, and that's typically represented here with different fiber lengths: 0 kilometer, 1 kilometer, 2 kilometer, 2 kilometer in red. You see that the bit error rate is increasing dramatically with respect to the other curve. at different feedback rates. Here you can see that when the dispersion is properly cancelled, we recover exactly the same chaos cancellation. So dispersion can be properly compensated. Okay, there is a traditional trade-off between security and decoding quality. Maybe I will talk this later. This is illustrated here. You get a worse decoding quality, but a better masking quality. Okay, this is the trade-off. We could demonstrate 10 gigabit per second with 10 to minus 7 bit error rate over 116 kilometers. And we also reproduce the 3 gigabit per second, and of course, we could achieve this time error-free transmission over 116 kilometers per second. Those are also typical optical spectra, and so on. So, security issue. Maybe the most hot topic in chaos communication. So, there are parameters, mismatch sensitivity, definitely. You have to know exactly the parameters to properly cancel the chaotic fluctuation. So the parameters, the value of the parameters are corresponding to the key. But this key is not so high with respect to standard key lengths of digital encryption system. There are in the literature successful parameter identification methods. If you are just looking at the chaotic waveform, there are some techniques that can be used to identify the parameters when you know the model. You need to know the model. Also, you need to have not too much noise. Also, you need not to have information. If you have information superimposed to the chaos, it's more complicated. Or, for the moment, as far as I know, it was not successful with information at high bit rate. There are also techniques with phase-space reconstruction, but all of those techniques are usually not considering a lot of noise, and they are rather successful, but only on numerically generated chaotic time series. But with experimental time series, as far as I know, it was rather difficult. Definitely, proper cryptanalysis is lacking. So we still need to construct tools to analyze how we can measure the security in such a system. When you have digits, there are standard tools, but those ones cannot be applied straightforwardly to nonlocal encryption system. So there is a few work definitely to do. So the good thing is that we do have a proof of principle of chaos communications at rather high speed. So it's operational. It's still to be investigated for security issues, but it's operational. A good thing also is that we have an extreme experimental versatility. The setup I showed you is a basic setup, but I will show you next slide what we can add to complicate the system and maybe to define properly an encryption protocol, as it is done for standard encryption system. Okay, now parameter masking architecture. The main drawback is the fact that you can identify, for example, the time delay through autocorrelation function or mutual information function and so on. So people are thinking about architecture that are allowing the masking of this parameter recovery. We cannot recover using standard techniques. Maybe there is other techniques, more sophisticated, but with standard techniques, there might be architecture with which the parameters can be hidden for the known techniques. Cryptographic protocols are definitely needed. For that, we need to investigate deeper information theory. And as a suggestion, I can show you this electro-optic phase chaos setup, which is much more complicated than previously. You do have several wavelengths, for example, which you can switch according to a digital key, which is to be defined as well, but which is intended to enhance the security and the key length of the setup. You can have dispersion module. The dispersion can be also a physical key. The dispersion is known on the transmission channel to destroy the cancellation. But if you inject this dispersion inside the oscillation loop, this could be also a key. And the eavesdropper has to know exactly the value of this dispersion, which is not known. This dispersion can be performed by a standard dispersion compensation model, or, for example, through the properties of a photonic crystal fiber, which has strong dispersion and strong nonlinearity and things like that. This can be added inside the loop. As long as we can replicate properly such devices, it can be honestly considered as a means to enhance the security. You can use multiple wave interferometer, and you can also use multiple delay line, feedback delay line, which can be switchable. Those are standard techniques in optical telecommunications. You have optical switch, fast optical switch. You can have a key which is ruling the switching time and the switching events according to a secret key. So you see that this architecture can have a much more complicated behavior, which will be, I expect, I hope, able to provide a certain level of security. Last but not least, this is the future, I hope. So we can also think about using electro-optic phase scales to build a mutual coupling nonlinear delay dynamical system. So this is typically what we propose to explore, among many other things, in the frame of the newly started Focus project. You can see, you can recognize maybe here the optoelectronic feedback paths of the previously described electro-optic phase scales. But this output is actually back coupled here. We can inject an error signal, which is corresponding to a signal to be analyzed. We can also extract the signals to analyze the response of this mutually coupled electro-optic phase dynamics. So there are plenty of ways to do actually optical processing, nonlinear optical processing, and hopefully to develop new tools for example, here for demonstrating the physical realization of liquid state machines and maybe many other applications. I thank you for your attention.
Thank you, Laurent, for the interesting talk. So if you have questions.
I made this question several times before, I'm not really of course, it will be very difficult to decrypt anything. You have different keys and different passwords. It will be difficult even for the receiver. But anyway,
maybe even for the receiver, but we assume that everything can be controlled within a sufficient accuracy, which was the case actually for the standard basic application.
But this was not my question. This kind of crypto systems have been open to some expert in neural networks or in this kind of artificial intelligent things. So has been this kind of methodology open to other people to see if it's really easy or difficult to hack this?
Yeah, we have a collaboration with the University in Santander with Pesquera. And Sylvia Ortin did a PhD thesis using neural network computing to try to identify the parameters. So the task was rather difficult. I have to say that she was rather successful. The main problem is the fact that we could only work with her in a low frequency domain. So we explored the encryption capability of the first setup we developed, which was with the wavelength scale generator, which is working at up to 20 kilohertz or gigahertz. So in a frequency domain where the physical analysis of the signal is rather easy. If you are now working with a very fast signal, you have problem with amplitude resolution, with time resolution, and this is not so easy. So it was rather time consuming to extract a sign modulation from a chaotic encryption signal. It was successful, I have to admit, it was successful. But I'm not sure that it will be so easy if we are working with more evaluated systems, especially with the last architecture we proposed, actually.
I would like to say that on that respect that, for example, time delay, it is typically very easy to be extracted on the dynamics.
In the current configuration.
In the current configuration, or even if in that configuration, even if you have two delays, usually through this kind of analysis, which you either look at correlations or delay mutual entropy or different techniques, you can extract the time delay. So the time delay usually can be extracted in the current configuration. Of course, it can be masked using other things more sophisticated, but then whether you can really reproduce all the dynamics or not, as Laurent said, for example, what Sylvia shows is that for the simple system, for the system simple Ikeda or the most model, you can get a neural network that reproduces your dynamics. Or said another way, you can get a neural network that synchronizes to your the message to your carrier class message, not as well as the authorized receiver, but good enough to extract the message, if the message amplitude is good. So then again, that poses a question on how good synchronize the authorized receiver to the transmitter, because if the synchronization is excellent, then the amplitude of the message can be decreased, and when you decrease the amplitude of the message, you pose more difficulties for the decryption. So,
you work yourself nicely on the security analysis of your systems. Still, you have a rather pessimistic statement on your transparency saying that there is no crypt analysis yet. What is, in your opinion, lacking for a crypt analysis? What would need to be done?
That's a very important point, actually. That I already tried actually to build a new project with professional scientists of the cryptanalysis. But those people are whether too busy or too far from nonlinear dynamics principle to have the will to investigate time exploring this subject. So usually they have not so honest attitude saying, no, it should not be interesting, and they don't want to do that. So they don't have any strong argument to say it's bad, and they don't want to cooperate to demonstrate if it's bad or good. So that's the problem. So it's really
but is it the problem because since it's not algorithmic, the standard tools do not apply?
They do not apply, but for sure they are to be defined. What should be the hypothesis? What should be physically possible? That's also something which is it's really difficult to talk with these people because we don't have the same language. It's encrypted also. They are talking with zeros and ones, and we are talking with continuously varying amplitudes. Then they want absolutely to convert the continuously varying amplitude into zeros and ones, which is rather natural. But then, what do they do with noise? Because we definitely have noise, and so on and so on. So there are many barriers which they don't have in the day-to-day work investigating the security of digital communication systems. Well, that's the big problem.
So once they have the chance to do
information
research but doing something new and they don't want it? So for once they have the chance not to continue with incremental research but do something new and they don't want it?
Maybe. Why not? I hope there is no difference in the audience.
Yes.
One question. So chronological distribution is safe because you can always identify if someone is listening.
So chronological distribution
is always safe because you can always see the error rate if someone is listening or not.
Yeah.
So could you use the nonlinear response here to embed a similar scheme?
So the physical principles are rather different. So it's difficult to say. So I don't know how we could do this, but definitely at the beginning you should be aware that the goal of QKD is completely different on the one here. QKD is key distribution. Here we use a key which is already distributed to encrypt a message. So that's rather different. The main problem of QKD is also that you are necessarily working with very low energy level. So you have to strongly amplify what you detect, and when you strongly amplify, you have very low bandwidth. So you cannot go very fast with QKD. So that's more or less symmetric with respect to public encryption and public key encryption and private key encryption. Public key encryption is rather fast, but not so secure. No, conversely. Private key encryption is rather fast, but it cannot distribute the key. And the problem with public key encryption, it's not so fast because it's rather time consuming to recover properly the data, but it can exchange a key. So usually the software like PGP are combining the two. First, to define a secret key through public encryption, and then use this secret key to apply private key encryption system, which is going much faster. So the best way would be here maybe to combine, as I often say, quantum key distribution and chaos communication. Quantum key distribution is distributing the key and the physical parameters, eventually
But
changing.
if you could use the chaotic response of the system, the instant change in the starting position would lead to a big change sometime later. So couldn't you identify if someone is eavesdropping on this?
Maybe, why not? I know that this is something which is investigated by the quantum information community. So they also try to really see if someone is tapping the line or not.
I would say that in principle there is one fundamental difference, and it's that at the quantum level there is the so-called quantum non-conic theory. So you cannot cone a quantum state without disturbing it. So if you are transmitting that, you are going to, if you copy during the transmission, you are out of the state no matter what you do.
Yeah.
From a classical point of view, you can do it. Whether that is easy or not to do it, whether that has influences somehow in the dynamics or not, that may be depending on your configuration. But in principle, nothing prevents you to take the state, copy, and resend it again. It might be completely complex, very difficult, or practically, requiring much more equipment than you might have. But there is not that, it's not forbidden. While at the quantum level, it is forbidden. And that's what they export. They can guarantee that, for example, this key has not been taken. Provided that it is done at the quantum level, photon by photon, or very few photons by very few. And this has no disadvantage. The chaos thing is seen being classical behavior, cannot provide that level. Still, that doesn't mean that it is possible that if you take the system in a way that is not proper, you distort the signal, and you might detect that somebody is tampering with the system or whatever. But it's just because you don't do it in the most sophisticated way.
Does this have any application to the wireless communication?
Yeah, it could be. So the principle can be transposed rather directly between the optical domain to the wireless domain. So you just have to change the devices.
Forgetting everything about optical, because I'm putting on a normal communication system then.
Yeah, using only electronic devices.
Yeah.
Yeah. We did some investigations using electronic chaotic frequency generator. Actually, this is possible as well. So you can generate a chaotic frequency modulation involving very similar principle. I can give you a reference, and I think I have to check. Also, for the secret, an old secret we did on that investigation. But that should be possible.
Okay. So, if there is no more questions, we thank the speaker again. Before we leave, let me announce that next Friday we have a seminar at 12, which is a unusual time for our seminars, usually in the afternoon, by Jordi. Okay, so remember, Friday we have another seminar. Coffee. There is coffee outside for the ones attending the meeting in person, and for the ones online, they can have coffee.